Definition 1. So suppose f of x is defined when x is near a number a. It's going to sound convoluted and go for it. That was underwhelming. I thought that was going to be way louder. It's my own pencil sharpener. Oh, yes.
Just the wrong one.
Okay. So, that was more what I was. Okay. So, the concept today is kind of a little far out there at first, and then it makes sense. So, let's pay attention. Also, a lot of the words that they use in calculus, a prof will say, they'll read it out and you'll be like, I have no idea what you just said. It's okay. You'll be fine because you took this class. So, definition 1. Suppose f of x is defined when x is near the number a. This means that f is defined on some open interval that contains a, except possibly a itself. Then we write the limit as x approaches a of f of x equals L, and say the limit of f of x as x approaches a equals L. If we can make the values of f of x arbitrarily close to L, as close to L as we like, by taking x to be sufficiently close to a on either side of a, but not equal to a. Perfectly clear, right? You now all know exactly what that is. So easy. Okay. Okay, so what the heck does that mean? It just means that whenever we take the limit of something, it doesn't have to be what the value actually is at that x value. It's what it's getting closer and closer to from the left and the right. So for example, this graph. I'm getting closer and closer to a, correct? And when that happens, I get closer and closer to a y value of L. Yes? That's from the left. From the right, I'm also approaching L. We agree? So I can say that the limit as x approaches a, labeling this graph as f of x, let's say, of f of x equals L. Because from the left and the right, they're both approaching L. Okay? It just happens that also x equals a is equal to L, because this graph just keeps going, right? This graph actually has a coordinate at a. It is L. That happens to be an add-on. But if that coordinate was open, a removable discontinuity, because we don't say point discontinuity anymore, we say removable discontinuity, we would still have the limit being there, because it's not what the value is, it's what it's approaching. So let's look at B. So as I approach A from the left, it's approaching L. We agree? As I approach A from the right, it's approaching L. True? So we can say the limit as x approaches a of f of x equals L. So it's the exact same limit. For this one, f of a equals L, because I have a coordinate there, right? The graph went right through. We agree? For this one, though, f of a equals something down here. Do you see that? We can label it as m, maybe. So for this graph, f of a equals m. I don't actually care about that when I talk about limits. Limits is just what it's approaching from the left and the right, not what that actual value is. So from the left and the right, they're both approaching L, so the answer is L. But f of a equals m. This one is the same f of x graph. From the left, I'm approaching L. From the right, I'm approaching L. So the limit as x approaches a of f of x equals L. So these all actually have the same limit, even though their graph is a little different. This is a continuous graph. This one has an open dot, a removable discontinuity, and an actual coordinate at f of a equals m. This one just has removable discontinuity. What is the value of f of a? It just doesn't exist. It can equal L, that's true. But f of a just does not exist. There isn't a coordinate at a. So all three of these have different coordinates at f of a, but that's irrelevant to limits. Limits is, what is it approaching from the left and the right? If the value at a is there, or not there, or somewhere else, it doesn't matter. Okay? So the limit is really kind of your end behavior as you're approaching that value. So let's look at this one. We have the limit as x approaches 1 of x minus 1 over x squared minus 1. Now I can't just go plug the 1 in, because if I plug the 1 into that equation, I'm going to get a 0 in my denominator. Do you see that? Which is a problem. So we'll talk about the table of values after. We're going to do the algebraically first. So I'm going to go the limit as x approaches 1 of x minus 1 over x squared minus 1. Now the limit as x approaches 1 continues to come along in every single step until I substitute that 1 in, or I'm allowed to substitute it. If I substitute it in right now, I'm going to get 0 in my denominator, and that's an issue. We can't have that. We can't divide by 0. But that denominator I can factor. So I get the limit as x approaches 1 of x minus 1 all over x plus 1 x minus 1. Now these cancel off. When they cancel off, in 30-1 we called that a point of discontinuity. We agree? In calculus, we're going to call it a removable discontinuity. That's what they call it in calculus. It drives the profs crazy that the Alberta curriculum calls it point of discontinuity. But it does, so you have to conform to what it is. Every prof from now on will call it a removable discontinuity. The reason why is there's different types of discontinuities. Removable discontinuity is technically a point discontinuity. It's just an open dot that's been removed. The other kind is a jump discontinuity, which, like, if it was, say like this, and then we came down here and we drew a graph like this. This is a jump discontinuity. I had to jump with my pen to draw the rest of the graph. Okay? So there's different types of discontinuities. So that's why we're more specific about removable or jump instead of point discontinuity. Now remember, these slash lines are just ones, correct? Every time you cancel, you're left with a 1. So in the top of this, I'm left with 1 over x plus 1. Do you agree? Still haven't filled in my x values, so I keep writing the limit. Now, like I said to you, the moment you can plug it in and not have an issue, you're allowed to. So the problem child in this question was that x minus 1 in the bottom. Because if I plug a 1 in, I'm going to get 1 minus 1, which is 0, which is going to make my whole denominator 0. We agree? That's the problem. I got rid of the problem now. So if I plug a 1 in now, is it going to come out as 0 anymore? No. So now I can plug the 1 in. And the moment I plug the 1 in for x, I don't have to write the limit as x approaches 1. That's the placeholder to tell you that's what x is. So the moment you substitute that in for x, you don't need that anymore. So the limit is going to go away now, this word, and I'm going to get 1 over 1 plus 1, which is 1 over 2. So the limit as this approaches, as x approaches 1 of x minus 1 over x squared minus 1, it equals a half. What did we just find? The y value of the what? The y value of the point is continuity, did we not? In 30-1, that was a standard of excellence question. If you had to find the y of the point is continuity. Remember what we did is we canceled off that x value, and then you could input it in because you got rid of the problem, you got the y. So technically, just a side note, if we had a graph like this, and then we had the graph go like this, correct? And this was 3. We agree? What we're doing when we're doing that is we're finding the point of discontinuity, the actual whole thing. So we're getting that this point of discontinuity is at 3, and let's say -2. We agree? So does that point actually exist on here? No, it's a point of discontinuity, aka, now forevermore, removable discontinuity. Okay? So the graph doesn't actually exist there. But that is the limit for this graph. If this was the graph, the limit is x approach 3 of f of x, my answer would be -2. It doesn't actually exist there at all, though, does it? But the limit, the definition of a limit, is not what the value is at that x value. It's what it approaches. So from the left, I'm approaching -2. As I approach 3 from the left, I'm approaching -2, correct? And as I'm approaching 3 from the right, I'm approaching -2. So that's why my answer is -2. So that's when you have a point discontinuity, aka removable discontinuity. When you find the y value of it, that is your limit, because that's what it's approaching from the left and the right. So we could do it algebraically like we just did. Sometimes we can't do it algebraically. This one we can. But we can also do it with a table of values. So can everyone type that into their calculator? X minus 1 over x squared minus 1. If you have one that doesn't do a fraction, you're going to have to put the numerator in brackets divided by the denominator in there. Everyone has it typed into their calculator, correct? So into our y equals, we have that. We want to get the y value that corresponds with that correlating x value, correct? What's the buttons we can press that we can input any x and kick out any y? Second trace value. Yes, every single time. So we go to our calculator, we put in that equation into our graph. And then we can go second trace value, and we can go 0.9, hit enter, and we get 0.5263, blah, blah, blah. Then I don't have to go back in. I can just put in a new x, right? So now I have 0.9. Now I just go 0.99 and hit enter again. Get 0.5025. If you're getting fractions, it's because you put this in as a fraction. So if you want decimals, you actually have to go to your y equals and put it in as x minus 1 divided by x squared minus 1. If you use the fraction button, it will kick out y values that are fractions. Yeah.
So could it have fractions?
You just won't, it's okay to have fractions, but a lot of people won't know what they stand for. You know what I mean? Like 0.50 is more obvious that that's 0.50 than some random fraction that's sitting in front of your face. Oh wait, then 0.999, you get 0.50025. And if I put in a 1, I get error, because it does not exist on here, correct? 1 is where we have an open dot. Now guys, before I do the rest of them, why the heck did I pick 0.9, then 0.99, then 0.999? Anyone know? Anyone have any ideas? Yeah.
You're slowly getting closer and closer.
That's that arbitrarily closer number that they were saying in the top, that paragraph that made no sense, right? We're trying to pick a number that's arbitrarily closer to the actual value, so we get closer and closer and closer on the left, and get closer and closer and closer on the right, and see if they reach the same thing, right? So 0.9 is quite a ways away. I know it seems like it's close, but it's still quite a ways away. 0.999, if I really want to get really close, I could go 0.9999999. That'd be really, really close to 1. Okay? Now I want to approach it from the, so that was approaching from the left. Now I want to approach 1 from the right. So if I go 1.1, that one's quite a ways away. And then if I pick 1.01, we're getting closer. And we want to get close, because if we're still, like 1.1 is still quite a ways away from 1. So guys, from the left, as I'm getting closer to 1 on the left, I'm getting really close to what value? What am I getting close to? Yeah, 1/2. And then this one I'm getting really close to 1/2. So what are they approaching, possibly? 1/2. Now, algebraically, it comes out legitimately at 1/2. It is 1/2. You have no choices. It is what it is. But your table of values, which is called numerically, it can help us to reassure that, or reaffirm it. It can also help us to visualize that that's what's happening. So from the left, I can see that this graph is a little higher. It's at 0.5, blah, 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 when I'm coming in. And from the right, it's a little bit lower, right? But they're reaching at 0.5 situations. Both of these are showing that it's 1/2, though, that they're getting closer and closer to, right? Okay. For this next one, I wanted to get close to 0. 0 is an issue, though, because 0 squared is going to be 0, right? So I know that on my table of values, this is going to be D and E. We're not going to do the algebraically first this time because it's a bit harder. I want you guys to do graphically. And if you look, From the left, I got closer and closer to 0 by making it negative 0.001. And then from the right, I got closer by making it positive. Okay? So everyone's typing that into their calculators. If you want it to come out as a decimal, which is what I would do, you put them in brackets and just put the division symbol between them instead of using the fraction button. Okay? So everyone try that out and fill in this table. So I'm going to type in negative 0.1, and I'm going to get 0.1666, blah, 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 blah. Then negative 0.01, I get neg 0.16666, and then negative 0.001, 0.16666. Okay. And then these are going to be the same thing. Okay. Now, unless you know what 0.1666666 repeated is in a fraction, you're probably going to leave it. So we're going to do it algebraically and prove that that is actually what it's going to get, the actual fraction. Okay? Now, we're going to all use our thinking caps. So here we have, up here, we could factor it and it would nicely cancel off, right? And our issue was the x minus 1. And we know it was x minus 1 because it is x approaching 1. X plus 1 would be 1 plus 1, which is 2. That was not our issue. It was the 1 minus 1 that got us a 0 that was the issue. Yes? This one's problem is this t squared. If I plug a 0 in, the t squared turns to a 0, and I'm done. Right? So if I'm going to solve these algebraically, the whole goal is to do something to the equation so that I can get that denominator, the problem in the denominator, to get out of my life. Because if I can get it to go away, I can just plug in 0 and I'll get an answer. Currently, that t squared is my issue, right? Need to get the issue to go away. So I'm going to rewrite the question always, because that's what we do. We don't work our question down from a question that's in there. We rewrite the question. That's our very first step. Okay. I'm not going to tell you anything. I'm going to ask you, what do we do? What could we do? I have a radical and a number. Subtract it. Any mathematical knowledge in your head that you think maybe we should do? It's going to be 0. Found it. My hint is you're going to have to multiply by something. Starts with a C. So close.
Conjugate.
Yes! Conjugate. You are going to multiply by the conjugate. Listening. Okay. I have a t squared that is in the bottom. That is a problem. I need to get that bad boy to cancel. Okay? I have a radical attached to a number. I cannot cross off anything when I have a radical attached to a number. That's one term. Remember, plus or minus signs between two terms make it one. They like sew it together. Remember in grade 11? Oh my gosh, grade 11 nationals kills me. You know, we had x over x minus 2. So many students, solved it out, negative a half. I'm like, what are you doing? Stop the madness. Okay, so when you have a plus or a minus sign, that is physically attached together, correct? The only way the x minus 2 can cancel is if you have an x minus 2 in the numerator. Those bad boys can cross off because they're twins. So whenever you have a binomial, which is attached by minus or plus sign, or a trinomial, the only way you can cancel them off is if you have a matching twin in the top, okay, or the bottom. So this here, guys, this currently, that's a binomial. That is only getting canceled off if I have a matching binomial. So this t squared is only canceling off if I have a t squared in the numerator, and currently I have a binomial with a radical in the numerator. Nothing's canceled, right? But we learned in grade 11 to multiply by conjugates. Conjugates are when you have one of them is a radical and one of them isn't, or both are radicals. The reason why we learned to multiply by the conjugate, which is the exact same thing, opposite sign, is because when you multiply by a conjugate, it gets rid of the radical. Right? So let's go to a basic conjugate. So say we had root x plus 2. If I multiply by root x minus 2, root x times root x, what happens? You get x, right? Whenever you multiply two radicals that are the exact same together, the radical sign drops off. because you'd actually get root x squared, and the square root of x squared is x, okay? Then, the reason why you multiply by the conjugate is the conjugate is opposite signs. Same terms, opposite signs, okay? So the reason why you do that is, oh my goodness, I'm still going to be left with a radical, and Mrs. Lepp, you told me the radicals go away, and you're a liar. No, just wait. Cool your jets. Root x times negative 2 is negative 2 root x. True statement, still a radical there. I'm not lying, okay? But the reason why you use opposite signs is 2 times root x is plus 2 root x. And because you used opposite signs, when you distribute, your plus and minus signs, those bad boys are going to cancel, right? And then plus 2 times negative 2 is negative 4, and my radical went goodbye. Out of my life. See you later. Sayonara. Okay? So, I need to get a t squared to cancel. The only way I can get t squared to cancel is if a t squared from the top or something like that. And the only way I can have that when I have a radical is to get the radical to get out of my life. And currently it's not. And the only way I can get it to go away is multiplied by a conjugate. Yeah? So that's why we learn these things. We learn these things so that we can actually think. Because the scary thing is when we send you off into the real world, and you can only do stuff because you're taught it. Right? You've been taught knowledge. Can we use it? That's what we need to know. So when we sit here, I don't always want to just teach you something right away. I want to ask around, see if someone can come up with maybe what it could possibly be. Well, if I need a t squared to cancel, and I got myself a radical, I need the radical to go away, and I have to dig into my repertoire in the back of my head. How did I get a radical to go away? I multiplied by the conjugate, and then the radical went away, right? So we have to use our knowledge that we've learned. That's what calculus does. It uses everything that you've been given and try and use it, okay? So I am going to multiply by t squared plus 9 under a square root. For some reason I didn't do that. Plus 3. Now, everyone put their pencils down for 2 seconds because a whole bunch of people will get stuck here if they don't listen at this spot. I need to get the t squared to cancel off. True? That's what we agreed to. So guys, if I distribute the t squared into this bad boy, is it going to be easily just able to cross off? No. So whenever you multiply by the conjugate in calculus, we say to ourselves, I need to get the t squared to cancel. So I'm going to leave it separate. So I'm not actually going to, this is going to equal the limit as t goes to 0. I'm not actually going to distribute the things that aren't conjugates. I'm going to leave them in brackets so that when I get a t squared, hopefully in the top, it can cancel off. If I distribute it into the other one, it's going to be now embedded, and now life is hard. You're going to have to remember to GC have a backup. So always remember that the ones that are not conjugates, we're going to leave separate because I need this out of my life. That is my current issue. And until it's gone, I have an issue. And I need to do out. So this is going to stay t squared plus 9 plus 3. And then I'm going to distribute the tops. I always distribute the conjugates because I want that radical to go away. I don't want a binomial. I need something that can go away. So let's distribute. So we get root t plus 9 times root t plus 9 is just, what? Root t squared plus 9. Root t squared plus 9 is just t squared plus 9. And then I get minus 3 root t squared plus 9 plus 3 root t squared plus 9. And they're always going to go away because that's why we multiply by conjugate, and conjugate meaning opposite signs, right? And then I still have my last two terms to multiply out, minus 9. Oh, goodness gracious. What do we have left on the top? T squared. What can I cancel off? My issue. And then my issue gone. Bye-bye. Okay. So, t squared, t squared. Now the whole top canceled off. So that doesn't mean I got a 0. I have a 1, because that's a 1 times a 1 times a 1 times a 1 times a 1. They're all 1s. Remember slanted slash lines, whenever you cancel off, those are just 1s. So we are left with, the limit as t goes to 0, of 1 over root t squared plus 9 plus 3. And I told you that the issue was that t squared. And if I can get it out of my life, maybe I can plug the 0 in, and now my life is better. Right? Okay, well, let's see. The moment I plug the 0 in, I don't have to write the limit anymore. The limit only comes along to tell me that t is 0, t is 0, t is 0. The moment I plug it in for 0, I don't need it anymore, right? So my next step, because I'm plugging in the 0, this goes away. So I get 1 over square root 0 squared plus 9 plus 3, which is 1 over 6. Guess what 1 over 6 is? 0.166666666666. Does that make sense? So remember, you guys, we don't want to do stuff by memorizing steps because you'll forget a step. And then you can't do the question. If you understand that the t squared is my problem, the only way I can get it to cancel off is if I have a t squared in the top and I have a radical, which is now my problem. How am I going to get that to go away? Then we're not memorizing steps, we're understanding, which is way better. Okay? Next page. Maybe. Okay. So here we have the limit as x approaches 0 of sine x over x. Okay? So what we need to do is we need to figure out what this limit is going to be. Can you guys type this into your calculator? And then we'll explain something why I have both graphs here. I always want to show you how you could do something, though, if you don't have a calculator sitting in front of you. Because maybe they take your calculator to university, right? Or they give you just a basic one, you can't pull a graph up. So I can see this by a graph. I can see that if you look from the left, it's approaching 1. And from the right, it's 0, it's approaching 1. So my answer is going to be 1. If you look like right from the left, it's getting closer and closer to 1. From the right, it's getting closer and closer to 1. So the limit would be 1. So I know the answer to this is 1. Okay? What you could do is you could use the two functions and then divide them out and see what it would be. You could do that as well. People get confused, though, because they're like, well, this would be undefined. It is undefined. Why is it undefined at 0? Well, first off, if I put a 0 in, it's a problem. Second off, the function sine x is this one. You know that. The function x is the straight line, correct? At 0, what's this doing? This is taking the y values at 0 and doing what to them? Dividing them. We agree? So it's 0 divided by 0, which is actually undefined. 0 divided by 0, because you're dividing by 0, you can't do. So if you actually look on the graph, you go to the table of values and you look when x is 0, it's not happy. It says error, correct? So even though this graph in front of you looks like it actually passes through the y-axis, it doesn't. There's a removable discontinuity there. And there's always removable discontinuity. When you plug that 0 in, we get a denominator problem, and those two don't cancel off, right? Or it's not a piecewise function, technically. Okay, so know the answer to that is 1. Then there's this one, the Heaviside function, or Heaviside, I don't know how to say it. You should Google it. You should Google how you say it, because I don't know. Heaviside, Heaviside, blah, 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 blah. We're going to go with you can read it and choose your own path of how you say that. Okay? This is what it's represented by. So fun fact, this function is named after the electrical engineer, Oliver Lepp. You choose. Go on your own path of how you say it. Okay? And can be used to describe an electric current that is switched on at time t equals 0. The reason why I gave you this is I want you to see that in calculus there are actual equations that represent different things. So calculus is taken in a lot of different places, and not just engineering, it's taken in a ton of different places. There's lots of SAIT courses that actually use calculus. They often have the word engineering behind them, but they're like a diploma. So like mechanical engineering diploma. I think there's quite a few at SAIT. And probably at NAEP too, the colleges. But they take these calculus courses because they have currents and stuff like that they have to be able to do the calculus with. They have to understand limits. They have to understand how to do derivatives and all that stuff. Okay? So, we want to determine the limit as x approaches 0 of h of t. So we have to draw this. Okay? So this, you guys have done piecewise functions. We've done a few of them. Yes? So this one says when t is less than 0, it follows the equation y equals 0, technically. And y equals 0 is the x-axis, right? So we know from 0 less, it follows 0, which makes sense. Until when you go to shut something on, it gets a current, correct? Before you flip on the switch, there's no current, which is 0. So we have an open dot here, and then it goes this way. Okay. Right? So this is an electric current that is switched on at time t equals 0. Then when 0 starts, the current is at 1. So it's equal to, so it's a closed dot, and then it runs this way. So the only examples I've given you so far of limits, from the left and the right, they approach the same value. Okay? Does this one approach the same value? No. So I want to show you something. The limit as x approaches 0 from the left, that's what this little negative means. It means from the left. Of h of t, because the function isn't f of x this time, it's h of t. So as it approaches 0 from the left of h of t, what y value is it reaching? So as I'm following 0 from the left, I'm approaching what y value? 0. So from the left it equals 0. Yes? Then the limit as x approaches 0 from the right of h of t, and we always need a function beside because we're following some sort of function, right? What does it equal from the right? 1. So there is a limit from the left. There is a limit from the right. And the limit just tells you what your graph is doing on either side of that point, right? Or a non-existent point, whatever it may be. So there's a limit from the left. It is 0. There's a limit from the right. It is 1. If they are not the same thing, the limit at that value doesn't exist. So I can have a left-handed limit. I can have a right-handed limit. But the limit as x approaches 0 of h of t on this particular one does not exist. So the key thing with limits is in order for a limit at that value to exist, the left and the right limit has to be the same. And in this case, it did not. It resulted in different y values. Okay? So here we're going to talk about one-sided limits. An example for you, notice that h of t approaches 0, t approaches 0 from the left and 1 from the right. We indicate this situation by showing what we did up there. I wrote it out already. The symbol t as 0 to the negative means from the left, and t 0 positive means from the right. It's just terminology. Okay? We're going to flip over. All right. Definition 2. This is what I literally just said. So the limit is x approaches a of f of x equals L, so a single limit, equals L, if and only if from the left it equals L and the right it equals L. So it's just what I just said, right? The limit can only exist if from the left and the right it equals the same thing. If from the left it equals L and the right it equals M, then the limit wouldn't exist at its value. So we're going to look at some graphs here. Example 5. This is the graph of G. I want you to tell me what these values would be. Use pencil. Try it out. Oh.
Thank you, Ms. Lepp.
You're welcome. All right. 2 from the left is what this one means, right? So we're going to go 2 from the left and we're going to stop at 2. What are we reaching? 3. Okay. 2 from the right. What are we reaching? 1. What's 2? Does not exist. Smart children. Okay. 5 from the left. 5 from the left, it's approaching 2. 5 from the right, it's approaching 2. Do we care what it is at 5? No. So the limit is? Okay. So this one I want 0 from the right. Not quite sure why I put left things on the table. I don't. We don't need these, but I put them. You're welcome. Anyways, I was nice, so I put the actual graph on. So let's talk about the graph. From the left, what's it approaching? Infinity. From the right, what's it approaching? Infinity. Just because they both approach infinity doesn't mean it approaches infinity. Okay, infinity is a concept. So when you have infinity, you do left and right. And the reason why we care about the limits as you approach infinity is it tells you how your graph ends on either side of asymptotes, right? You guys, for the most part, just type into your calculator 30-1 and poof, spit out what you saw, right? But here, we're going to learn more information about how to draw a graph in the third unit. We learn how to draw a graph without our calculators at all. It shows us using derivatives how that calculator gets a graph out. Okay? So, the answer to this one, the limit is x approaches 0 from the right of 1 over x squared equals infinity. Now, this one, we couldn't ever do algebraically because you can't get that x squared. There's like nothing to do, right? So you have to look at your graph. Or you could do a table of values and get closer and closer and closer to 0. All right. Example 7. We have a piecewise function here, okay? I want you guys to draw the piecewise function, and then we're going to talk about the limit as x approaches -1 and 1. But first draw it. Shh. If we look at the actual graph that is sketched here, there is a gap, a jump discontinuity at -1, correct? The moment there's a jump discontinuity, the left limit and the right limit can exist, but the limit itself won't, because they have to go through the same value. From the right, this one is approaching 0. From the left, this one's approaching 0. From the right, this one's approaching 1. They're not approaching the same thing. However, this one at the 1, they're both approaching the same thing, correct? So the limit at 1 is going to be 1, because they're both approaching the same thing. From the left, it's approaching 1. From the right, it's approaching 1. Therefore, it is 1. So that's how you can show it with your graph. But how do we show it with actual equations? So we're going to do 1 and -1. So we'll do -1 first. So we have to do the limit as x approaches -1 from the left of f of x. And then we're going to do limit as x approaches -1 from the right of f of x. Well, what the heck f of x do I use? If it's from the left, that's less than, correct? If it's from the right, that's greater than -1. So I just have to use the right equation that works with that. So from the left, instead of writing f of x, I'm going to go the limit as x approaches -1 from the left. Which of these equations is from the left of -1? Really the top one, right? The 1 plus x. The one that is less than -1. Because less than -1 would be coming from the left. Correct? And the easiest way to remember it is if it's from the left, you pick the less than. If it's from the right, you pick the greater than. Okay? So this is my less than one. So instead of writing f of x, I'm actually going to put 1 plus x. And then my next step is to fill in the -1. When I fill in the -1, the limit word goes away. Right? That's the point. Substitute in, it goes away. So I get 1 plus -1, which is 0. So from the left, it went to 0. Look, from the left, it went to 0. Same thing, right? Now we're going to do the one from the right. So we're going to do the limit as x approaches -1 from the right. Now I'm going to pick the greater than 1. This equation in the middle is when it's greater than -1 and less than 1. So this is going to work for the left of 1 and the right of -1. I'm going to use that same equation. Correct? So I'm going to fill x squared in here because I need greater than -1. This is greater than because you read from the variable. Then I can plug it in, so I get -1 squared, which is 1. Now as I approach -1 from the right, it went to 1. So it's the same thing, right? The graph shows it's actually at 1. Now, because those are different, I say therefore the limit as x approaches negative 1 of f of x does not exist. Because they're different. There's a right limit, there's a left-sided limit, but there's not a limit. The next one, I can see that they're both actually approaching the same thing from the left and right, so the limit will exist because I have a graph that shows me that, but we have to show it algebraically. So, I'll come back in a second. So we're going to go the limit as x approaches 1 from the right, which, or not right, negative, 1 from the left. Which one are we going to use for the left? A less than 1 equation, right? Which one has less than 1 in it? This one has x is less than 1. Do we agree? So that's the equation I'm going to use, the one from the left. So I'm going to get x squared. And then I'm going to plug in the 1. So I get 1 squared, which is 1. Then I'm going to do the limit as x approaches 1 from the right. So now I need the equation where x is greater than 1, right? This is the one where it's greater. So that's from the right. I'm going to use this one, 2 minus x. And so I'm going to get 2 minus 1, which equals 1. They both equal 1. Let's look. From the left, this one's approaching 1. From the right, this one's approaching 1. They both approach 1. So what's the limit as x approaches just 1, not from the right or left? It is 1, because they're both the same answer. So therefore, the limit as x approaches 1 of f of x equals 1. Because they both have the same answer. If there's a jump discontinuity, the limit doesn't exist. Okay? If there's a point or a removable discontinuity, the limit will always exist. Because from the left and the right approach the same thing, even if it doesn't exist yet. Okay? This is your homework. Try it out. Call me over if you're a lost soul.